Okay, so today is 3.9, day 1, and it's derivatives of exponentials and logarithmic functions, with an emphasis on exponentials today. Monday, you will do probably the hardest derivative problems that we've seen all year long, and I think you'll like it too, because it's not that hard, but they are the hardest ones. So that means you guys can handle just about anything after this section. So what we're going to do today is stuff like this, guys. We're going to take the derivative of e to the x. We're going to take the derivative of 3 to the x. We're going to take the derivative of things like e to the cosine x. We're going to take the derivative of things like, I don't know, e to the tan squared x. This is the kind of stuff you'll be able to handle in about 40 minutes. You'll be able to do these problems. Okay? On Monday, what we're going to do is these kinds of problems. Watch close. You'll be able to take the derivative of ln x. You'll be able to take the derivative of log base 2 of x. You'll be able to take the derivative of log base 6 of square root of x squared, or some plus 1 or something. Lots of goofy stuff involving logs. That'll be Monday. And then, I think you'll really appreciate what we're going to do at the end of Monday's lesson. We're going to find the derivative of x to the x. Okay? So, the reason this is interesting is, if you look at it, it's kind of hard to tell what kind of problem it is. When you first look at it, you're like, is that like something to the x, or is that like x to the something? Do I start by bringing the x down and taking away 1, or do I do what Mr. Shore is going to teach us with exponential stuff, where x is the power? Okay? That's a very good question. This question needs to be rewritten before it can be solved efficiently. So, I think you'll find the lesson on Monday especially exhilarating. Things like x to the tan x, we can solve that. We can even solve x to the tan x to the e to the x. The derivative of that. So that when this section is done, the sky is the limit. And the limit is the derivative. All right. We need to do one limit before we can understand this lesson. And it's kind of a tough one to prove. If I were to prove this limit for you, it would take the whole rest of this slide and some more, and a lot of our time. So I just want you to get your graphing calculator out and type this thing in. Obviously, you're going to type it as e to the x minus 1 over x. And then you can use a table or look at the graph and see what you think the limit is. Okay, you might want to zoom out once. Okay, so if you look in your table, right? So I'm going to set the table on my calculator here. If you plug in like 0.1, when x is 0.1, this comes out to 1.0517. If you plug in 0.01, you get 1.005. If you plug in 0.001, you get 1.0005. So it looks like the limit as you go from the right of 1, or right of 0, excuse me, is 1, right? Let's try numbers slightly negative. So how about negative 0.1, negative 0.01, negative 0.001. What would that do? This is 0.95163. This is 0.99502. And this is 0.9995. So I am pretty sure that this limit is what? What do you guys think? Pretty sure that this is 1. If x is approximately 0, right? So we write that like this. The limo of e to the h minus 1 all over h equals 1. Okay? Now, we want to memorize this one. Okay? So that one we're memorizing. And the reason is, just like sine x over x, remember we memorized that one? This one does show up on the AP test sometimes. So make sure you have this one well memorized. I'll write a note. Nemo, right? So, okay? I believe that's Italian for memorize. But I could have just made that up. Okay. So now we know limo of sine x over x, and we know limo of e to the h minus 1 over h. They're both 1. Okay, so let's talk about e to the x. This is the graph, right? Does it look differentiable to you? What do I mean by that? When I ask that, what does that mean? Definitely continuous, and plenty of tangent lines, right? Any spots on there where you think there might be a sharp turn or corner or cusp or vertical tangent? I don't think so. Okay, so as we know, e to the x is an increasing function and it appears to be differentiable for all x. Okay, in fact, it appears to be where if you draw tangent lines, all of them have a positive slope. Right? There are no horizontal tangents on here. That's why it's 1 to 1, and that's why it has an inverse, and its inverse name is ln, right? But how do we find the derivative? If it has slopes, we should be able to find the slopes, right? So how do you do that? Okay, you guys remember the definition of a derivative? Been a couple weeks since we've even needed it, because we've been learning derivative shortcuts. But you know how you learn a new derivative if you don't know it already? You do the definition of derivative and see what it comes out to. Okay? Okay, so let's do the definition of derivative. How does it go again? Limo f of x plus h minus f of x all over, yeah, x plus h minus x, or just h, right? So how do you apply that to this problem? If f of x is e to the x, what would the difference quotient look like here? Wouldn't it be, well, don't forget the limo up front, but the difference quotient part is going to look like this. E to the x plus h minus e to the x all over h. How in the world are you ever going to get the h to cancel so that you can, you know, plug in 0? Isn't that kind of the goal most of the time? So it's all about how you rewrite things, okay? How do you rewrite e to the x plus h? Can you think of another way to rewrite what I have here in green? There is another way to write that. Yes, we could throw some natural logs in here, but we don't really have an equation, so it seems a little unfair to be doing that on an expression. If you had an equation, you could do that to both sides or whatever. That's actually a really good thought. We will need that trick on Monday. Just think algebraically. What if I wrote this? X to the a plus b. You might think, oh, x to the a times x to the b, right? So what is another way to write e to the x plus h? E to the x times e to the h. Okay, so let's try that. Let's see what happens. Anyone see anything interesting happening here? Yes, we can factor out an e to the x. Cool. You mean factored out to the front, right? Like that? Okay. Well, can we pull it all the way out of the limit? Can we put it in the front? That's called the front. Can we do that? Absolutely. There is no h in it. Okay, this is an important principle. If this had been a phi, you would feel no qualms about pulling it out. Right? Pull it right out. Why? Because it doesn't depend on h. We could pull that e to the x all the way out to the front, because it doesn't have any h's in it. Right? As far as limos go, when h is going to 0, e to the x is just a number. It's like a constant almost. So we can write it like this. Didn't we just do this limit on our calculators? What was it again? 1. Interesting. So what is the derivative of e to the x? E to the x. The derivative of e to the x is e to the x. That's pretty fascinating. Is it the only function like that? I want to say yes. Yes. Pretty neat though, isn't it? Okay, so you guys remember why? You remember I was telling you a couple weeks ago that you might not like radians that much. You might prefer degrees. Because we all think like 360 degrees, 270 degrees. But do you remember I told you that the derivative of sine is cosine? But only if you're using radians? You might remember me saying that. If you're using degrees, the derivative of sine is not even cosine. Okay? So it turns out that radians are very convenient for mathematicians. It's not a matter of preference. It's not like centimeters and feet, centimeters and inches, that kind of thing. It's with trig stuff, radians are the way to go. It is far more convenient to use radians. And here we can see that of all the different bases that we've ever studied in your algebra classes, remember you studied 2 to the x, and you've studied 3 to the x. You've even done problems with money where it's like, 1 plus 0.04 over 12 to the 12t if you're doing like finance stuff. And the base was like 1.0, whatever, 0, I don't know, whatever that is. But of all the different bases we've ever studied, it turns out e to the x is the most interesting and most convenient one. Because when we're doing derivatives, e to the x is the one whose derivative is itself. And the other ones are not like that. So in a minute we'll talk about 2 to the x and 3 to the x and those ones. But e to the x is its own derivative. Isn't that cool? Okay, so what does this mean graphically? Let's go back to the picture for a second. It means that this point right here is, of course, the point 0, 1. But that's not all. The slope is 1. And this point here, as you know, is the point 1e. But that's not all. The slope is what? E. In other words, the y-coordinate and the derivative, the slope, are exactly the same everywhere. You see? Over here, this is the point -1, comma, e to the -1. But the tangent line has slope e to the -1. Very interesting. Very special graph. And that's not all, of course. If you take the derivative a second time, the derivative of the derivative is still e to the x. In fact, it's the only function where you can take the derivative an infinite number of times and it never changes. Just is always the same exact function. This will be a big, important thing later, too. Okay, now, what would happen then if you're taking the derivative of e to the u, and it was u that you were taking the derivative of? Like, that's your differentiation variable. Wouldn't this just be e to the u? Yeah. Okay. What happens when you're doing d dx of e to the u? This is when you need the chain. Okay? You would just do e to the u times du dx. Of all three of these, I probably would memorize the last one, if I were you. Okay? It's really just the chain rule. If you're good with chain rule and you never, ever, ever forget the chain rule, you can just memorize the first one. But if you're the kind of person who sometimes forgets to use the chain rule, you might want to memorize the last one. The one in the middle is just a restatement of the first one. It just reminds us that we don't always use x for a variable. Okay, so let's go on and try some examples. So the first example I chose is e to the x squared, and we're just going to try and take the derivative of that. So we'll start with the fact that it is primarily e to the something, right? Looks like e to the something. So if it looks like e to the something, then the derivative is going to be the original. But the chain rule is in effect. The chain rule is always working. If you haven't taken the derivative of x squared yet, you aren't done. X squared is nested inside our e to the x function. So we are going to now have to do derivative of that. And that's the answer. Okay, so the answer is e to the x squared times 2x. Let's try another one. I have a ton of examples, so try to copy quickly. Yes?
Wait, so e to the x and then x squared, it would be the same thing? It's still e to the x?
The derivative of e to the x is e to the x.
Right.
The derivative of e to the something is just e to the something.
Okay. So
But the chain rule is in effect. So we still need a 2x either way. Because that's just the derivative of x squared. You can't just forget about it.
So it's really e to the x times 1?
Yeah. Yeah, that's right. The derivative of e to the x, if you go back a page, the chain rule is always in effect, right? So when you look at the blue one, when you take the derivative of e to the x, right, the answer is e to the x, and then you're supposed to look up here and say, ooh, what's the derivative of that? Which is just 1, so we never really write that. But technically, I guess you should. You should write e to the x times 1. It means you're considering the chain rule there, it's the derivative of x. Is that your question?
Yeah.
Yeah, good. Okay. Is this a hard problem? Not really. If you knew that e to the something just recycles itself when you do the derivative, you just copy and paste that there, and then you just say, okay, what was that function that was nested inside the e? Well, that was x squared, so just attach the derivative of that at the back. Or put it in the front. Some people like to write, they'd rather write 2x e to the x squared, which is, I think, how your TI 89 will display the answer. Who has the TI 89? Have you tried the derivative of e to the x squared on there? It should write it the way I just circled it, I think. So I just chose a ton of variety on this, okay? So let's keep moving. We're on to a new one now. This is primarily a product rule, okay? So the first thing you should notice is, hey, this is a product. That's important. Don't look at this and say, oh, there's that e to the x Mr. Shore was talking about. No, you look at it and say, there's a product rule we talked about 5 weeks ago. Okay? So first and foremost, it's a product. And it has a u function and a v function. So we start with u prime, v, and then we'll do v prime u. So for u prime, that's just 1. V, we just copy and paste it in here. V prime is going to be the toughest. This is your v right here. So what is the derivative of that thing? Well, that's an e to the something. So that would be recycled into the answer. It's going to be part of your answer. The question is part of your answer. Times, and then what's the derivative of negative x squared? Negative 2x. Okay, kind of makes me wish I had more parentheses and maybe even some brackets here. Let's make these brackets now. And then we just have u, that's just copy and paste from up above, so that's just x. Okay, so here's the answer. E to the negative x squared plus actually it's minus 2x squared e to the negative x squared. And it's very common to factor out whatever you can in a product rule. So I would factor out the e to the minus x squared. Does anyone know why we do that? We don't have to do it, but do you know why it's probably a good idea?
So only have to plug it in once.
So you don't have to plug it in. Oh, yeah, if you're going to plug in like 2 or something, it's a little bit easier to plug numbers in once it's factored. Yes?
If you want to do the second derivative?
Yes. If you want to go on and do the second derivative, you're dealing with a problem that's not too much harder than the one you started with. But if you're expanding this sucker all the time, you're going to have multiple terms in your second derivative. This is going to be a little bit cleaner than it would be if you did it from this up here, this phase. Okay? All right. Let's go on to another example. Oh, actually, we need to talk about this first. What about 2 to the x, 3 to the x, or even just a to the x in general? What are we going to do with that? Okay, so if the derivative of e to the x is e to the x, then does that mean that the derivative of 2 to the x is 2 to the x? I wish. It's not like that. Okay? So let's talk about what to do in this case. Let me show you how the rule came about, and then you can just memorize the rule. Okay, so imagine trying to take the derivative of 2 to the x. Right? You cannot use the e to the x rule for it, and we're really not very interested in doing that definition of derivative thing, because we don't really like that much. So what we're going to do is cheat. We're going to rewrite this as, I'm going to write it as e to the ln of 2 to the x. You're like, what are you doing? I wrote 2 to the x as e to the ln of 2 to the x. E to the ln of 2 to the x is 2 to the x. Right? Don't these just cancel? Okay, so you're like, man, you just made it messier. Yeah, but I made it into an e to the x problem. It's an e to the something problem primarily now, see? Okay, so that was a little cheat to get it to look kind of like e to the something. By the way, we can just move this x right here to there. That's just one of the rules of logarithms. Okay, so now let's go ahead and take the derivative because we know how. We did it just a few examples just like this. So first and foremost, this is e to the something, so it will contain this in our answer. Then we multiply by the derivative of what's upstairs. So what do we have going on up here? ln 2 times x? That's like 0.6 something times x. It's just a linear expression. The derivative of x ln 2 is ln 2. Right? ln 2 is a number. It's like mx. What's the derivative of mx? M. So it's ln 2 right there. And then this I will cancel out. Oops. I'm going to have to do something first. I can't cancel out quite yet. I'm going to move this x back up to here. And then cancel this out. So the final answer on this, I asked you, what do you think the derivative of 2 to the x is? And you might have said, oh, 2 to the x, because that's the way e works. You were close. It's not 2 to the x, it's 2 to the x ln 2. Okay, so here's what we're saying. We are saying that, get rid of this random box down here. Go away. Okay, go away too. All right, here's what we're saying. If you're doing the derivative of e to the x, the answer is e to the x. If you're doing the derivative of 2 to the x, the answer is 2 to the x times ln 2. Does anyone care to guess what the derivative of 3 to the x would be? 3 to the x times ln what? 3, yes, that's right. In other words, here it is, here's the rule. d dx of a to the x is a to the x ln a. Yes?
Can you explain cancel e to ln. Like,
Yes. E to the something and ln of something are inverse functions, right? E to the x, ln x, they're opposite ideas. So if I give you a number, let's say 5, and you perform an ln on that, and then you e it, you're going to get 5 again. It's going to go back to being 5. So this is true for expressions also. If you do e to the ln of blah, 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 that's like, it's like squaring the square root, or cubing a cube root. These just undo each other and it just becomes 2 to the x. Listen, the red part is not important right now. You can learn that again in Calc 3 if you need, or refresh it yourself. It's in the book. But listen, what's important is what I circled at the bottom there. I'll circle both rules of the day so far. They're right here. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x ln a. I have a question for you. How come when we do d dx of e to the x, we don't need the ln e thing? Why not put an ln e right here?
That equals 1.
Yes, ln e happens to be 1. See? So it's just not necessary. You're welcome to write it if you like. But if we don't need to, then let's not. You know? So, okay. Let's go on. How many of you, by the way, knew that the derivative of e to the x was e to the x? Did anyone know that coming in this year? I had a first period student who knew it. You probably know who that is. Yeah, because he was curious. He's a very curious mind. He wanted to know, how do you handle this function? You know? How do you handle that function? He's always asking me stuff, and he's researching on his own. But he did ask this. 2 to the x is a little different. 2 to the x is, 2 to the x ln 2. Okay. So don't forget the chain rule, and don't forget the ln2. So everybody watch this problem. This is primarily a 2 to the something problem. 2 to the something ln2. That is not the chain rule, that is the rule. Okay? So it's going to be 2 to the x squared ln2. What's the ln2 doing there? It's part of the package. It's always there when you do derivative of 2 to the something. Now you multiply by 2x. Okay? It's part of the rule. The derivative of 2 to the something is 2 to the something ln2. Always. That's why I have it in green. That goes together, always. You can't separate that green. That's the way it is. Let's go on to the next problem. Okay, let's take a look at this example. This is the derivative of 3 to the something. So you would actually start off by doing 3 to the something ln 3. That is just the derivative structure for 3 to the something. And then we look and see what our argument is. It's a cotan x. Put that in there. And we need the derivative of cotangent, which happens to be negative cosecant squared x. Okay, and then maybe we can just put this in some kind of logical order. ln 3 is a number, so we'll put that in the front. There is a negative, that goes in the very front. And then maybe we can do cosecant squared x next, and maybe 3 to the cotangent x last. I'm not sure the order matters all that much in reality. Whoa, what is that?
product rule.
Good, good. First and foremost, a product rule. Yes, very important. Okay, so we have a u and a v. It looks like u prime is going to be the ugliness. So I'm going to give myself a really big first parentheses. I might need a bigger one. Let me do even bigger than that. I might even need brackets for that u prime. That thing's awful. Okay, so u prime is going to be in brackets, and then I'll have v right here. And then v prime, that's easy. That's just cos x. And then u, that's just copy and paste. And yes, it's 2 to the 3 to the x, and then plus 4x squared.
Are you ever going to give us a problem like this?
Yes, I like this problem. I like this problem a lot. It tests you on all the rules, except, yeah, it has the trig, it's got everything. This is a good one. It doesn't have any ln's in it. Maybe I'll throw that in there. Okay, so we got to work on that u prime here. So what is u prime going to be? Well, primarily u is 2 to the something, right? So it's going to be that exact same junk times ln 2. Good. Very easy to forget. The 2 to the junk ln 2 goes together. Okay? It's part of the package. Now we need the derivative of this stuff that's up here. This 3 to the x plus 4x squared. That I need the derivative of that. So the derivative of 3 to the x is what?
3 to the x ln 3.
Good. 3 to the x ln 3. And the derivative of 4x squared is 8x. Okay, and then remember I had suggested that we do some factoring if we can. I noticed that there's only 2 terms here. These 2 big blues. Okay? I'm going to pull this out real quick. So it's going to be like this. 2 to the 3 to the x plus 4x squared. And then what I have left is I've got a 3 to the x ln 3 plus 8x times ln 2 sine x plus a cos x. Pretty ugly, but that's what it is. Okay, if you're interested in seeing a word problem, it is in the period 1 video. I may have to go back and fix something if I did the derivative wrong earlier today too, on the previous example. Okay, so for our last example, we have a word problem. I'm using the one in the textbook, one of the problems in the book. And it says the spread of a certain flu, except it's spelled flu wrong. There we go. The spread of a certain flu in a certain school is modeled by this function, where P of t is the total infected population and t is the number of days since the flu first started spreading. Fix the spelling there too. There we go. Okay, estimate the number of initial students infected, or students initially infected, or initial number of students infected, however you like to word that. So, first thing I'm going to do is plug in 0 for time. Okay, so P of 0 would be the initial population that's infected. So this would be 200 over 1 plus e to the 5 minus 0. So there it is. And if you type this into your calculator, you will find out what it is. It's like 1.339. This would just mean one person infected. So the entire flu began with one person being infected. That kind of makes sense. Okay, now let's go on and do part B. It says, how fast is the flu spreading after 5 days? Okay, so that's more of an issue of the rate of change, right? So we're trying to find P prime of 5. So first thing we have to do is find the derivative of P. Okay, so first we need to find dp dt. And so we're going to be taking the derivative of 200 times 1 plus e to the 5 minus t to the minus 1. So I'm writing this fraction using a negative exponent. Okay, the 200 can just pull out. We'll watch their language there outside the room. Okay, we need them to watch their language. All right, now we're going to go ahead and take the derivative of this. This is primarily something to the minus 1, as you can see. So we're going to do 200 times, and then we're going to bring that minus 1 down. And then it will become a minus 2. We subtract the power, right? And then we look at the fact that we have an inside, which is 1 plus e to the 5 minus t. So the derivative of that will be 0 for the derivative of this part. And then the derivative of e to the 5 minus t is e to the 5 minus t times the derivative of the 5 minus t, which is just negative 1. Okay, so it turns out I can just use multiple parentheses here. And I'm trying to plug in 5, so I say we do that as soon as possible before we mess this all up. And we have 200 times, okay, you'll notice that this -1 cancels with this -1 in the back. It's all multiplied. And we really just have 1, let's change to blue, 1 plus e, because I'm plugging in 5 actually, so it's going to be 1 plus e to the 0. I'm plugging in 5 for the t, right? Times, and then it's just e to the 0. So this gives me 200 times 2 times 1, which is 400. 400 what? 400 people per day. 400 people per day are being infected on the 5th day. That's pretty staggering. This all started with one person, but by the 5th day, 400 people per day were getting sick. Okay, so what's going on is the population is increasing of sick people. Population of sick people is increasing, but also the rate at which people are getting sick is increasing as well. So you can also try going back a few stages and plug in other amounts of days. I was using t equals 5 right here. But you can try other things, like what happened at, p of 1, or p prime of 1, you can plug in 1 there, you can plug in 2, 3, 4, and see what happened during the first 4 days, and you'll see that it has been growing significantly. That's the end. Here's your homework.